So we had started talking about section 2.4. Of course, we got done with the basic operations, addition, subtraction, multiplication, division with functions, and then we were talking about how to work with compositions. And remember, with composition, we were basically talking about how you take one function and you put it inside of the other. So the idea is you start solving with the innermost function first. Whatever results you get from it, you apply that to the outer function and solve that. You can have, of course, composition between two functions, but we had also seen an example where we can have composition between three functions. Sometimes you can actually look at, I would say maybe complex functions, something that are can be basically broken down into simpler functions. So if you look at something like this guy over here, f of x equals x minus 7, the whole quantity squared, we can actually break it down into simpler functions. So basically you can see if you were to, if you were given a value for x, where would we start? We would start by substituting x. The first thing we would do is subtraction, right? We would solve inside the parentheses first, and then we would do the square outside. So the idea is the function can be broken down into two operations. You have the subtraction that's happening, so that's the x minus 7, and then you have the square that's happening on the outside. So you can actually break it down into two simple functions. So if we're defining f of x as x minus 7 and g of x as x squared, that means your f of x function has to go inside. So that would be the second function that you would write, and the function that's outside is the first one that we put in this notation for a composition of functions. So f goes on the inside, g on the outside, and this is how we would break it down. Now, if you were to switch the order of the f and g function, so instead of putting f on the inside and g on the outside, if we reverse that order and put g on the inside, f on the outside. Now remember, g is the square function, so that means you would put the square value inside. And this would end up giving you x squared minus 7, which of course is not the same as the original function you started out with. So again, it's important what order you keep on your composition. So this example over here is kind of asking us to do the same thing. They're giving us the capital K of x function, and they're asking us to break it down into three simpler functions. So let's talk about what operations are happening. So if you had a value for x, which would be our starting point, what's the first operation you're going to do? We've got 2 on the outside, which means you're multiplying by 2. You, of course, also have the square root, and then you have the subtraction. So what's the order of the math you would perform? Where would you first start? What operation would you do first?
Subtraction.
You would do the subtraction first. Okay, and then once we're done with the subtraction, what would be our next step? Square root. And then multiply by 2. Very nice. So those will actually define what our three individual functions need to be. So we would do just kind of going in the order. We can do f of x as our subtraction function, so that would be the x minus 3. Then you are doing the square root, we'll call that g of x, and that would be just square root of x. And then our last one is where you multiply by 2, and we'll call that the h of x, and that will be you're multiplying something by 2, so 2 times x. So remember, x minus 3 happens first, then the square root, then the multiplication. So what would be the order of our composition so that we can get our capital K of x function? So the order of your f, g, and h, what composition order would be? What's the innermost function, then the outer function, and then the very outer function?
Would you put f of x inside, and then g of x, and then h of x?
Okay, so f of x inside, then g next. and then H at the very outside. Okay, what do you guys think? H on the outside, G in the middle, and F in the very center? Yeah, let's see if that works. Ooh. Okay, so if we are doing H of G of F, that means H on the outside, G on the inside, F on the very inside. This should come out to be. So replace your f of x with the x minus 3. So what this tells us is now you are going to take the x minus 3 and you're going to put it inside the g function, which means wherever you see an x, you replace it with x minus 3. So that would end up giving us again h on the outside. If I'm replacing my x with x minus 3 in the g function, this guy should come out to be square root of x minus 3, and that's kind of what our capital K function had. So far we're on the right path. Then the last part is you take this and put it inside the H function. So now we're going to take the H function, which is this guy here, and you're going to replace your x with the square root of x minus 3. So that would be 2 times x. And you're replacing that with square root of x minus 3. And again, you can really get rid of the parentheses here. Is this the same as the function where we started out?
Yeah.
Yeah, so that tells you this order works perfectly for us. So H on the outside, G in the middle, F on the variance. So the order really does matter. Now, if you change any of the positions of H, G, and F, it's going to give you an entirely new function, which will not be the same as that capital K. So please be very careful, when you're kind of working through these composition examples. So let's see if we can pull something from my MATLAB here. There we go. Did we do something with set of ordered pairs last time? Did we not? Okay, I thought we had, but maybe we didn't. Okay. So let's see how composition would work if you're working just with a set of ordered pairs. So here, they're giving you F on the outside, H on the inside. And they're just asking you to find F of H. So this is, in generic terms, not for a particular value of X. So in this case, what you would do is you would start with F of H. So start with the H function and use the first X value that you see inside the H function, which comes out to be -6. So H of -6, which means you're trying to find the Y coordinate for the X, right? So what is H of -6 going to give us? Yeah, very good. The Y value that goes with it. -8. Okay, now you look at the F function and then try to find the ordered pair with -8. So what will that give us? -9. Very nice, because this is the ordered pair it takes you to. So you are going to end up with 9. So this ordered pair for the new function, the composition that we are creating, you started out with -6 as your first X value. And by the time you simplified the whole composition, you got 9 as your answer. Okay. Repeat the same process. And this time, we're going to put the second ordered pair in the H function. So that would be H of 1. And again, what will H of 1 give us? Sorry,
Negative.
not negative, right? Just
9.
Oh,
9. And then you go back. Yeah, very nice, Maria. Go back to the f function, and what do you have for f of 9? F of 9. So you have to look at your x values. So, Maria, Diana, I see you guys are coming up with -8, but where are you finding the negative? Because there's no 9, right? You've got -1 for the x value, -8, and you've got 1, right? So you have to look under the x values to find the 9 before you can find its pair for the y value. Does that make sense? Yeah, okay. I'm just going to say does not exist because there's no answer for f of 9. We don't have an x value of 9 in there. And you only had 2 ordered pairs in the h function, right? So there's nothing else we can do. So the only answer we came up with was that first ordered pair of -6 and 9, and that's all we had. So that's what we're gonna put in here. So if that was the only answer, Maria, and you did not have the first ordered pair of -6 and 9, then we could say undefined, but in this case, since we have at least one ordered pair, that's all we're going to use for the new function. Alrighty, so let's see, we need parentheses. And in the parentheses, we have -6, 9. Okay, let's check that. Wonderful. Okay, so this was obviously just to show you how it would look like if you were working with a set of ordered pairs. Now, obviously, most of the time we work with function definition. So let's look at an example with this one. And this one, as you can see, does give us the 3 different functions to work with. Okay, so they are giving you f, g, and h functions. They're giving you the composition of g of h of f. But they're specifically asking you to do this for an x value of 4. So let me see what answers you come up with for this guy. And then again, those of you who are online, please share your answer with me through chat so I can make sure you are comfortable with this. So start on the very inside and you're going to be using 4 as your x value. Do we have an answer?
Yeah. So,
I actually haven't solved this one, so I'm going to sure. Those of you who are online, what did you guys come up with? Okay, Ricardo, I see your answer. Oh, Diego. Okay. So I've got 20 and 50.5 from your classmates online.
I got 20 as well.
You got 20 as well?
I got 20.
You got 20?
Yeah.
Okay, and I think I saw one of you had a 14 there.
No, I had a 16.
And you had a 16, okay. So let's see what this is supposed to come out looking like. So we're gonna start with f of 4, so that's this function here, which means you are replacing your x value with 4. And that would end up giving us, and I'm gonna do this on the side, I guess. So we're gonna start by finding f of 4, which will be 4 times 4 minus 2, 4 times 4, of course, will give us 16, 16 minus 2 will give us 14. So 14 becomes the input now, right? So then you will have g of h, and now you're going to be replacing your f of 4 with the answer we came up with. So that's gonna be the 14. Okay, which means we're done with the f function. Now you get into the h, right? So now you're gonna be doing h at 14, which is this guy here. So replace your x value with 14 and 14. So what will that give us? Alrighty, so you are doing h of 14, which is 14 plus 2 divided by 4. Very nice. So 16 divided by 4 will give us 4. Okay, very nice. So that means, oh, it's not gonna let me. So let's see, that means we are now replacing h of 14 with 4, which is going to become your input to the g function. So g of 4, let's see, this guy here. So that becomes 4 for the x value, which will be what? 4 squared plus 4. And you can see that's where the 20 comes from, right? So 4 times 4 is 16, 16 plus 4 will give us 20. Okay, so Maria, you also had 20. Diego, what do you think happened? Because you had a really large number there. Okay, you see where you went wrong? Okay. So Luis, what do you think happened? Why were you at 16?
So I did the 4 squared, but I didn't add 4. You know, like,
Oh, so you just got that last
I
part.
didn't even see that. I didn't even see it.
Okay, okay. Anybody else question on this one, like where you went wrong or what happened? Alrighty, so this one specifically wanted the answer. There we go. That's gonna be a 20. Alrighty, good to go. Okay, this one is not asking you to find a specific answer. This one is just saying, let's do the composition. And then let's talk about what kind of domain our new function will have. So this one is giving us f of g, so f on the outside, g on the inside. Like I said, you're doing this in generic terms, not at a specific x value. So we're just finding f of g of x, which means you take the g function and this will replace the x inside of your f function. So the way this guy works is you have g of x is defined as 1 over x. Okay, so everywhere that you see an x, replace that with 1 of x or 1 divided by x. So we are given square root of 2 times x, and you're replacing your x with 1 divided by. And just clean that up. 2 times 1 is 2. You end up with square root of 2 divided by x. So just general generic terms. That's the first part. Then they are asking you for the domain. This one we need a square root. Square root of 2 divided by x. Any ideas on what the domain for this guy would end up looking like?
Be 0 to positive infinity.
0 to positive infinity, okay. And of course, you know, we're talking about this new function here. Of course, infinity always takes parentheses. What about 0? Include, not include?
No,
And why is that?
because you can't put zeros.
Very nice. Since my x is in the denominator, we cannot put 0 as included, right? Because if x was equal to 0, you would end up with an undefined. So any number larger than 0 would be fine, just not including 0 itself. All righty, perfect. So let's do this. This would be parentheses 0, infinity. And then any questions on this, guys? So as I was kind of talking about earlier, you know, you're basically creating a new function over here when you do composition, bless you. All right, Maria, very nice. So not, Diana, it's not really about 0 can never be included, but in this specific example, yes, because your x is on the denominator. We don't want to divide by 0 because remember division by 0 is undefined. And so that's the reason why we're not including, but if you were having a different type of example, then 0 could be included. So I wouldn't say never included, but in this example, definitely not included. Yes, Maria, exactly. So whenever your x is in the denominator, anything that would make your denominator equal to 0, you have to leave those numbers out. All right, guys, let's see. What do we have next? Okay. So here, they're defining the individual functions h, g, and h. They're giving you a capital H function and they're asking you, out of the 3 given to you, which one of these would compose together to form the capital H function? Do we need all 3 of them? Do we just need 2 of them, 1 of them? What would it look like? So which 2 functions, 3 functions, 1 function would give you the capital H of x? G and H.
Yeah, yeah, G.
Very nice, yeah, very good, because here we have x minus 6, which of course is this guy here, and then you have the square on that, and this guy gives you the square. So yeah, those 2. There's no absolute value symbol in the original capital H function, so we don't need to use f, which means these guys are out. Yeah. So A, B, C, or D, which option would give us the capital H function? D. B as in boy, D as in dog. D as in dog. D as in dog. Okay. Anybody else? This is what Della is going with. A?
A or B.
No, because don't you have to put the subtraction first?
Very nice. Remember how you would solve this if you knew the x value, right? So you would have to do the subtraction first and then the square, because if you knew the x value, the first thing we would do is the subtraction. So we would have to subtract first. And then we would come outside and do the square. And because of that, because the g of x function is subtraction first, we will go inside and the square function will have to go outside, and that's why it's going to be option D here, and it couldn't be, because you know, if you did the G on the outside and H on the inside, just to show you what this would look like,
It'd be backwards.
it would be backwards. So H on the inside means square goes on the inside. And then your G is x minus 6, so this would end up becoming x squared. So you would actually then have to do the square first, right? If you did G on the outside and H on the inside, we would do the square first and then subtract, which of course does not give us the order of this. So I would say just, you know, write it out like we did and see which one matches the original function you're trying to find the composition for, and that way also you can eliminate the wrong options. And we definitely did not need 3 compositions of, you know, the same function. So yeah, very nice. It does actually come out to be option B over here. Any questions on this one, guys? Anybody online have a question about this? Okay. All right, perfect. Okay, so this is also a composition, and the reason I've included this because, you know, it kind of doesn't tell you you're doing a composition, but they do tell you you're given 2 functions and you have to write y as a function of x. So of course, as you can see, this is a different function with the y value in it. This is a different function with the x value in it, and they're telling you it's got to be y as a function of x. So that tells you we're still looking at composition, and they basically want us to write it as y equals x, you know, something. So how would we do that composition? So where do you think, how do we combine these two so that y equals, you know, something as x? Do you put this guy inside this one, or do you put this guy inside this? Which direction do we go in?
Would you put the Y inside the W?
Okay. If you're gonna put y inside the w, how would this substitution happen? Because how would we have to rewrite this so that you can put it into this function here? You're given y equals w squared minus 1. Okay, Diana, you are saying we need to put w into y.
That's
And
what
then Diego and Maria, looks like you guys have x plus 4 squared minus 1. Okay, let's take a look at this. So your classmates online are saying to go the other direction, take this function and put it into y. Della, okay, so let's see, you have y equals, since this guy has w and this one is w, that's where the substitution will happen. So we've got w squared minus 1. This is what our y function looks like. And since we are substituting
Oh, you said.
this in for the w, that means your x plus 4 will actually replace the w. And you can see, yeah, it does actually get us to what we were hoping for, y equals x, you know, something. So that would be the transformation you want to happen, because what's going to happen the other way is there's going to be a lot of rewriting, right? Because you would have to get w by itself before you could make the substitution happen. So it would be easier to go in this direction. That way you don't have to do a lot of rearranging. And is that all they wanted? Looks like it. So x plus 4 quantity squared minus 1. So let's see, parentheses, x, there's my plus. Plus 4, close our parentheses again. Raise this to the second power. And then minus one. Oh, so take my exponent. Right, let's check that. That looks good. Okay, questions on composition in general, guys?
Doesn't matter if we do that or if like we square the x plus one. Like if we do it in the other one,
Like go ahead and FOIL it or
Yeah,
do
FOIL.
the opposite order?
no foil. Doesn't matter.
You could, because you would do, if you did the FOIL. Okay, Diana, the reason we got rid of the W squared is because that's where the substitution happened. So what we did here. Because we have to write Y as a function of X, what we are basically doing is we're taking this definition for W. They're telling us W equals X plus 4, right? So we're literally taking the W squared here and we're substituting for W, which they're telling us equals X plus 4. So you're actually not getting rid of the square term. You are just taking W using this definition and you're replacing the W with X plus 4. So you will see the squared is still there. We didn't get rid of the square. We just replaced it with X plus 4. So it's kind of like if you knew what the value of, W was, you could just substitute, if W equaled, I don't know, 5, we would go ahead and put it in the function. That's the same thing we're doing, but just replacing it with X plus 4. Yeah, so that's what Alexis was asking too. You can go ahead and FOIL this and simplify this if you want. So if you wanted to FOIL this guy, this would come out to be, what is that, X squared plus 8x plus 16, and then subtract 1 from it, which would give us X squared, 8x, 15, and that will also work as an answer here. So yeah, if you wanted to simplify it, you can. I just left it without simplifying it.
On our exam, would it matter which way we do it?
Not really, it shouldn't. Anybody else, any other questions on this?
Can we do an example as an absolute value one?
As an absolute value one? Okay, let's take a look. Was that something you had in homework?
No, I was just wondering if we could do it because I get confused with the absolute value.
Okay. Okay, so if you were gonna be doing a composition. I don't know, give me some function here for Y. Whatever comes,
So we could do like the same problem just as an absolute, like.
okay, if you wanna do it that way, let's see, Z. Let's do Z squared plus 5Z. And then we can define Z as. We want something with absolute value. Okay, so if you're defining Y as Z squared plus 5Z and Z as absolute value of X minus 4. Same idea, right? You take the Z, put it inside the Y function. So in that case, everywhere that we see a z value, you would be replacing it with this second function over here. So if you have y equals z squared plus 5 times z, which of course we actually don't need to see there. So I'm just kind of creating the template because I know we're supposed to square the z value here and then 5 multiplied with z. But now you are replacing your z with absolute value of x minus 4. And then you would just need to simplify this. So what do we know about square? What does the square value do? When you have a positive number, what does square do when you have a negative number? So if you had -4 and you square it, what would be there?
Positive.
Okay, and if you had +4 and you square it, what would you get?
Positive.
Positive as well. So a square basically gives us a positive answer no matter what. So actually what happens then, because you have the absolute value symbol and the square, you actually don't need to use the absolute value symbol here because the square also is giving you positive answers. So you don't wanna, have to worry about the absolute value sign and the square. So we're just gonna actually replace that with x minus 4, the whole quantity squared. However, nothing like this on the other side. So this one will stay 5 on the outside. An absolute value of x minus 4. Now, again, if you wanted to, you can go ahead and FOIL the x minus 4 to the second power, but the absolute value of 5 times x minus 4 will stay the same.
So you wouldn't do anything else, you just.
Not with the second half. Yeah, now with the first half, like I said, you can definitely go ahead and clean that guy up if you wanted to. So if you wanted to FOIL him, this would give us x squared minus 8x plus 16, but then this guy would still stay 5 times absolute value of x minus 4. So again, either one of these answers would be fine. So you could leave your answer in this form or in this form. So either one of those formats would be okay. Question on this, guys? So absolute value, of course, works a little bit differently just because we know it's a symbol that gives you both positive and negative distances, depending on which direction you're going in. Okay, let's cancel you out. So that's actually what is happening in section 2.4. That's kind of where we end. Again, this is an application problem just to show you how compositions work with an application, but basically addition, subtraction, multiplication, division, and then composition of functions is what you're looking at in this section. All righty. Our last section in chapter 2 is 2.5. Now, in your D2L, you will see I have included section 2.6 also, but it's an optional section and we're not going to be working on it. But in case you guys were interested in knowing about direct and inverse variation, that's what 2.6 is about. But you have no homework, you will have no exam questions, anything from 2.6. So this is the last section we're doing in chapter 2. This one is inverse functions. So basically, when you think about inverse functions or even the word inverse, what comes to mind? Just basic definition. Like, what do you think about when I say inverse?
Inverted.
Inverted,
Opposite.
opposite. Anybody else? The opposite is probably what I would go with. So when we talk about addition, what's the opposite of addition? Subtraction. So that's an inverse function. So addition and subtraction are inverse functions of each other. Multiplication, division are inverse functions of each other. Like it talks about here, square will undo a square root. So a square root function and a square function are inverses of each other. So that's basically what we're looking at in this section over here. And this example kind of talks about two things that we are looking for. What is a one-to-one relationship? Because that's important if we can find an inverse function. And then, of course, what's that invertible property that we're looking at? So we started out with a basic pizza example here. I'm sure these prices do not apply in 2022. But we're saying if you can get a basic cheese pizza at $5, and each topping is going to cost you $2. So if you go with just the cheese pizza, no additional topping, that's gonna be your $5 price, right? Let's say you got one topping on it, maybe pepperoni or something. That's gonna be additional $2, which means your pizza will now cost $7. If you got two topping, pepperoni and I don't know, onion or something. Two toppings, that's $4 additional dollars, so 5 plus 4 gives you 9, right? So depending on the number of toppings, the price of your pizza will change. So you will see here, there's basically a unique relationship between the number of toppings and what the cost will be. So it's not like I can get one topping or two toppings and it will still cost me $7, right? One topping will cost me $7, two toppings will cost me $9. So there's no repetition between the dollar amount or the number of toppings. So that's what we're talking about when we're talking about one-to-one correspondence. So for $5, there should only be 0 as the number of toppings. For $13, there should only be 4 as the number of toppings. There can be no repetition between them. So that's that one-to-one relationship that we are looking for when we're trying to find the inverse functions. So, they're talking about a dollar menu at any of the fast food places, McDonald's, I guess Wendy's, Taco Bell, anything else. So dollar menu is the idea that for $1 you can get a drink, right? $1 you can get fries, $1 you can get probably a small size burger or slider or something. So each of these different food items have the same dollar price, right? So that's not a one-to-one relationship. You should only have, like I said, for $1 amount, one item, $1 amount, one item, which we will not see at dollar menu. Now, once you have that one-to-one relationship between your X and Y variables, the idea is, and you can see the definition for the one-to-one over here. The idea is I should be able to interchange my X and Y variables. So here you will notice my toppings are the Y variable, the cost of the pizza is the X. If I switch that relationship and make my toppings the X value and my cost the Y value, I am still maintaining that one-to-one relationship, right? My topping is still 0, my price is $5, my topping is 3, my price is $11. So that relationship transfers. So what we did by interchanging our X and Y variables, if this guy was the original function, he is the inverse. It's literally that simple. As long as you can establish that you have that one-to-one relationship between your X and Y coordinates, and you literally just switch your X and Y variables, you have created an inverse function. So when we are defining an inverse function, we are saying the function has to be one-to-one. If your original function is f, the inverse function is read as f inverse. And it looks like you're giving an exponent of -1, but that's not an exponent. That's just a notation we use to show that we are talking about inverse function. So your original function would be f, and its inverse would be f inverse, okay, with that little exponent. And like I said, you are basically creating the inverse function by interchanging your domain and range. So they want us to basically think about, would these examples here have that one-to-one relationship, which means would our function be invertible? Would we be able to find an inverse for this function? So let's talk about the first one here. The function that pairs the number of days since your birth with your age in years. So basically we're looking at two quantities, the number of days since we were born and our age in years. Can that be a one-to-one relationship, which means for one value, there can only be, so one, how many ever days it's been since we were born, and our age in years, there should only be that one-to-one relationship. There can be no overlapping. So let's think about this, and we can do this math pretty easily, right? The year you were born, the month you were born, the day you were born. From that, if you had to calculate your number of days, we would have whatever those number of days would come out to be, probably smaller for you guys compared to me, right? But you would have your number of days. So if you know that number, and then your age in years, whatever that might be, 18, 19, 20, 40, whatever that might be, would that be a nice one-to-one relationship? So for the same number of days, can we have two different ages? So if you were born, which none of us are that young here, but if you were born for like 1,000 days since you've been born, would that only give us one specific age? Yeah. So if you think about this, if you are, do I have a calculator here? Yeah. If you were born in 2000, that's been what, 22 years at this point, right? So if you took 22 years, multiplied it by 365, about 8,000 days since somebody was born, if they're born in 2000, right? So if we say it's been 8,000 days since this person was born and they are 22 years old, that's definitely a one-to-one relationship. Now, if you only knew the person's age, would you be able to calculate their number of days? No, why not?
Because it depends on like the actual day. Like it was in.
Yeah, because you wouldn't know what month they were born in, you wouldn't know what exact date they were born on, right? You just know they're 22 years old. Well, there can be a whole bunch of people who are 22 years old, but we wouldn't be able to calculate backwards and come up with their age. And it's not even so much about calculation, but if two people have the same age, does not mean they have the same exact number of days since they were born. Right? Because if somebody was born in January of 2000 and then the other person was born in December of 2000, I mean, they're almost a year apart at that point, right? I mean, 11 months apart. So you can imagine they're going to have different days. So that's actually not a one-to-one relationship. Those of you who are online, does that make sense, guys? Why this is not a one-to-one and we would not be able to find an inverse for this? Okay, so just keep in mind, number of days will help us calculate the age, but just knowing the age in years will not help us calculate the number of days. And additionally, it would not be a unique relationship because two people, like I said, 40, if two people are 40 years old, we really cannot calculate and say they're going to have the same number of days since they were born. Okay, so this guy is not inverted, because it is not one-to-one. Now, the second one is kind of using the same idea of number of days, but they are saying this function is pairing the number of days that a deposit of $100 earns interest at 6%, which is compounded daily. And by compounded daily, we're basically saying your interest is being calculated every day. So you're taking the number of days that we leave this money in the account with the amount of interest your deposit earns. So the number of days and the amount of interest, will that be a unique relationship? So if you leave the amount of $100 in your bank account, it's getting 6% compounded daily for 30 days. So 30 days, and then how much interest you earn, would that relationship be one-to-one? Would it be unique? So that way, if I knew the number of days, I can calculate the interest. If I knew the interest, I can calculate the number of days. Yes? Anybody who feels no? And the key thing here is how your interest is being earned, right? If your interest was being earned annually, which means once a year, then it really wouldn't matter if you had left your money in there for 30 days or 60 days, right? Because it was going to earn at the end of 365 days, or basically at the end of a year, it wouldn't matter. But because your interest is being calculated on a daily basis, that's what tells you this is a unique relationship. So the key word here was actually that interest being compounded daily. So based on the number of days is what your interest will be calculated in. So yeah, if you knew the number of days, you could find out what interest you have earned. If you knew the amount of interest, because we know interest is calculated on a daily basis, we would be able to find the number of days. So this guy actually is 1-to-1. So this guy is invertible, which means we can find its inverse function. Whereas with the one above that, we could, so that's what you're looking for, maybe. So that was just in terms of, relationship between two variables. Now you can see we also can try and identify if you have a 1-to-1 function looking at set of ordered pairs. And then of course by function definitions also, but let's go back 1 minute quickly to that definition of what a 1-to-1 function looks like. So here we are saying if your function has no two ordered pairs with different first coordinates and the same second coordinate. So here we are saying for two different x values, you cannot have the same y value. So this definition is actually different from what we had seen in section 2.1 when we were talking about if you have a function or not, right? If you have just a relation or if you have a function. In that definition, we had said for the same x, we could not have two different y values. This guy is saying for two different x values, you cannot have the same y value. So your y value should not be repeating, basically. And that's what you are looking for when you look at these examples here. So when you look at number 1, where your ordered pairs are -1, 0, 1, 0, and 5, 0. But there's different x values, we cannot have the same y value. So obviously this guy is not invertible, right? Because you have the same y value on all 3 of them. So if it's not invertible, you cannot find its inverse. Number 4, your ordered pairs are 1, 1, 2, 4, 4, 16, 7, 49. Is this invertible? Yeah, because you don't have a repeating y value in this case, so this guy is invertible. And then to find its inverse, remember you exchange the places of your x and y variables. So of course 1, 1 will stay the same. But the next one will become 4, 2, 16, 4, and 49, 7. So literally just interchange your x and y variables and you have your inverse function. Number 5. No, why not?
You have two same y values for different x values.
Yeah, very nice. Right over here in these two ordered pairs, you have two different x values, but the same y value, which makes this guy not 1-to-1, which means it's not invertible. And the last one, number 6, 3, 3, 2, 2, 5, 5, 6, 6. For different x, we don't have the same y, right? So this guy is invertible, which means you can again find its inverse. And an inverse happens to be the function itself, right? Because you have repeating x and y values. So he is his own inverse. Does anybody know what a function like this is called? When your x and y values are the same? We kind of talked about this a little bit in terms of equations back in chapter 1. This is what you would call as an identity, right? Because your x and y values are the same. So this is actually in equation form. That's what it would look like. Alrighty, guys. So that was just identifying if you had an inverse, an invertible 1-to-1 function or not, and if you could find its inverse. Now here, they're giving you the original function f. They're asking you to find the inverse, and then they're asking you to solve a couple more based on once you find your inverse. So let's take a look at our ordered pairs here. You've got -3, -3, 0, 5, 2, -7. So is this guy invertible? Yeah. So since it's invertible, we can find its inverse. Which in this case, your inverse, the first ordered pair will of course stay the same. Second one, obviously. In the first one, you just can't say that we've interchanged our -3 and -3, but we have. And then 5, 0, and -7, 2. Okay, now that you have your inverse function, the next part, so we took care of this guy, the next part is asking you to find the inverse at 5. So go to the inverse function, find the ordered pair, and what will our answer be for F inverse at 5? Yeah, very nice, because this is the ordered pair you are looking at. So that will give you 0. Then they are asking you to do a composition between F inverse and the original function F. And we know it's a composition, right? Because of that little open circle in there, multiplication would just be a dot. So this means composition F inverse will go on the outside. F of 2 will go on the inside. So can you tell me what F of 2 will give us? So that's the original function F, right? Go ahead, Jen. Sorry. Yeah, very nice, because again, F of 2 is talking about this ordered pair over here. So F of 2 gives us, sorry, -7. And this becomes the input for the inverse function. And what is F inverse of -7? Because F inverse of -7, this is the ordered pair you are looking at. And this guy. Give you 2. So that's actually not a coincidence that we started out with 2. And we ended up with the 2. Because when you do composition between a function and its own inverse, you do actually get an identity. And you will see this a little later on in this section. So Diana, when you are doing the very first one here, so when you did F of 2, then that means you're going to the original F function and you're finding where your X value is 2, right? So in this case, the X value is 2 and -7 is the Y value. So that's where this -7 comes from. But now that we are doing the composition inside the inverse function, so with the inverse function, this -7 now becomes your X value. So then you go to the inverse function, you find the ordered pair where -7 is your X value, and then you choose its pair, what the Y value is going to be. So the -7 changes positions. In the original function, it's the X value, but then when you put it in the inverse, it becomes the Y value. Okay, because you remember that's how we came up with the inverse function, right? We had to interchange the X and the Y variables, and so what was originally X will now actually end up becoming Y in your inverse function. So that's just kind of how those relationships work out. Della?
So if you use your original function in the inverse, it will always become out to an identity if you have like an actual number.
Yeah.
So then we could easily solve the problem no matter what.
Yeah, exactly. So you start with 2, your answer is going to end up becoming 2 for this composition between the function and its inverse. Diana, does that make sense? Yeah, okay. So you've got another example which looks very similar to this one over here, guys, and again, you can see that in the video lecture if you wanted to, but let's get into a different example here from my math lab. So here they're actually asking us to determine if a function is one-to-one or not, and your handout does talk about how to work through these types of examples. Oh, before we get into that. So since you are interchanging your X and Y variables to come up with your inverse function, that means your domain and range will switch places too. So what is the original domain for the F function ends up becoming the range for the inverse function. So whatever were the X values for the F will now become Y values for the F inverse. So Domain for the original function becomes the range for the inverse, and then of course, range of the original function will end up becoming domain for the inverse. So just basically keep in mind, since you switch the x and y values, the domain and range are also getting switched. So remember we had talked about the vertical line test when we were looking at if we have a function or not. In that same sense, we can actually use a horizontal line test to try and see if we have a one-to-one function or not. And can we find its inverse or not? So it's basically the same concept. Your horizontal line should cross your function only at one point. If it crosses at more than one point, you do not have an invertible function. It's not one-to-one. You cannot find its inverse. So of course, as you can see, absolute value crosses at 2 points. So this is not one-to-one. We cannot find its inverse function. But when you have x to the third power, so a cube function, the horizontal line only crosses at 1 point. So it does have an inverse. And of course, for the x cubed, cube root of x would be your inverse function. So that's kind of how the horizontal line test would work. However, sometimes don't depend on the graph only. Yes, horizontal line test is good to have, but if you have a function something like this, and this is the function x to the third power minus 0.01x. So if you were to put this on a graphing calculator, this is what it would look like. But if you were to zoom in closer to the origin, you will see when we draw a horizontal line to this, it crosses at 3 different points. But when it's in this kind of position, you draw a horizontal line through that, it looks like, okay, it only crosses at 1 point, we are good to go. But it's right at that origin where you see we have this little hill and valley, which is making it not a function. So that's why we obviously don't want to depend solely on visual checking to see if we have a one-to-one function or not. So this is kind of where we come into this idea of, if I put in 2 different values for x, am I going to end up with the same value of y? Which is basically what a horizontal line test does. So if you think about graphically, what does the horizontal line tell us? So when you're looking at the horizontal line, you can see we're going to have the same y value, but you would end up having 2 different x values, which defeats the one-to-one definition. For different x values, we cannot have the same y value, and that's what the horizontal line tells us, that if you have 2 different x values but the same y value, our function is not one-to-one. And that's kind of what we are doing algebraically. So you can see we started out with 2 different x values, but they still ended up giving us the exact same y value, which makes sense, right? It's a parabola, x squared, which again is going to fail the horizontal line test. So a parabola is not going to be a one-to-one function, but, and we'll talk about that here in a little bit.
Well, can't a parabola be on its side?
On the side would work, but you can also, where is it? Somewhere over here. There we go. This is what I was looking for. But you can take something like a parabola and restrict its domain. So we know a domain for an x squared function goes from negative to positive infinity. That's all real numbers. That gives us our little, parabola shape, which looks something like this. So the idea is, if instead of keeping our domain at negative infinity to positive infinity, what if we restrict it and we say, you know what, I am only going to look at x values from 0 to infinity, including x, which means instead of looking at the entire parabola, I'm only going to look at one side of it. And you will see by restricting our domain, we will pass the horizontal line test. Well, for the same for different x values, we're not gonna get the same y value. So by restricting our domain, this is what this function would then end up looking like. And we know for an x square, a square root is its inverse function. So you can actually modify your functions to make them invertible, for them to have that one-to-one relationship, and then you can find their inverses. Unfortunately, absolute value, you can't do that either, because that's just the way the absolute value function works out to be. So let's take a look at how we can find if a function like this is one-to-one or not. So as you know, you saw in your handout, you can do the two different values of x and see if you're gonna come up with the same value for y. But that can take experimentation, because how many x values are we gonna try before we find out which ones will give us the same y value? So instead, what we do is use algebra to help us out. So the idea is we are going to take our function and replace the x with x sub 1. So you're kind of creating a different x value, but not actually using numbers. And we're going to set this equal to f of x sub 2. So we're basically saying you have a different x value on each side. So you've got x1 and x2. Now we have to show, are they going to be the same x values, or are they going to be different x values? So what we're going to do is take our function definition and replace the x on the left-hand side with x1 and on the right-hand side with x2. So this guy will become x squared plus 1 times x. I'm just going to write it as x. On the other side, we will have, again, replace the x with x2. So this guy would be squared plus 1 times x again. So just have that as x2. And remember, our goal here is to try and see, even though I'm starting out with two different x values, do they actually end up becoming the same x value? And if they do, then we know our function is one-to-one. Anything we can combine together or eliminate? Now remember, x1 is different from x2. They're basically two different x values. So anything that can be combined or canceled out. So Maria, we are just coming up with x1 and x2. They're not coming from anywhere. That's just how you check algebraically to see if you have two different x values, or are they the same x value. So it's actually right over here. I'm trying to see where. Okay, so it looks like I actually don't have it in the handout. Okay, so basically, Maria, this is kind of where it's coming from. Now, in this example, we did actually use two different x values just to show that you were still ending up with, the same y value. So your ordered pairs here would be 1, 5, -1, and 5. And what this basically is telling us, even though we started out with two different x values, we still ended up with the same y value. So we know this function is not one-to-one, which means you cannot find its inverse. But instead of using, different x values, we basically just say, okay, what if we just use x1 and x2 instead of, worrying about which two x values will give us the same. So you're doing this more in a general algebraic sense instead of actually using numbers. So that's why we're just getting the x1 and x2 from, just to show that they are two different x values. And then you will see, once we were down here, Obviously, there's nothing we can combine over here, there's nothing canceling out over here, so this is actually telling us these two cannot be equal to each other. Now, if we could prove that x1 was equal to x2, then we would say this function is 1-to-1. Additionally, obviously, if we were to use a horizontal line test, and this one is a simple enough graph that we can use the horizontal line test, and that of course shows us it's going to fail being a 1-to-1 function, then yeah, definitely this guy you can use the visual test also. But with some examples, the only way we will be able to check is by using this idea of x1 equals x2, and this is actually one of those examples here. So this one, we would do the same thing, but again, our goal is to show x1 equals x2. If we can, which didn't work out in that first example. So if anything that can be combined or canceled out, then it will actually show you if we can prove that x1 equals x2, then that tells you your function is 1-to-1, which means we can find its inverse. That's what we're looking for. So that's the same thing we're going to do here. We're going to take b of x1 and set it equal to b of x2. So wherever you see your x variable, on the left-hand side, make it x1, on the right-hand side, make it x2. So that would end up becoming 12 minus x1 divided by x1 minus 4. Set this equal to, again, 12 minus x2 divided by x2 minus 4. So obviously you can see we have two fractions, left-hand side and right-hand side, so we can use cross product actually to simplify these guys out. So that means I am multiplying 12 minus x1 with x2 minus 4. On the other side, we'll be multiplying 12 minus x2 with x1 minus 4. And we will need to use FOIL on both sides, guys. Okay. Okay, so let's see, FOIL, we are going to do 12 times x2. We are going to do negative, so positive times negative is negative. 12 times 4 will give us what? 48. And then of course you're going to be multiplying negative x1 times x2. And then the last one would be negative times negative will give us positive 4 times x1. Okay, so this comes from your left-hand side. Repeat on the right, so this will be 12 times x1. Same thing, 12 times negative 4 will again give us negative 48. Negative times positive is negative, and again it's x1 times x2. And then the last one would be negative times negative is positive. So that would be positive 4 times x2.
So it's the same.
So again, we want to see what can we cancel out. So we can of course add the 48, which will obviously cancel each other out. What else can be canceled out here? What's the same terms on both sides?
x1, x2.
Very nice, yeah, the product of x1 and x2. So since that's minus, we can add. And this would also be add. So when we're trying to move it to the other side, your x1, x2 will also cancel each other out. What else can be moved around? What similar terms do you see on both sides? Well, we've got something with x2 on the left and right, and same thing with the x1, right? So try and combine like terms together. So I'm actually gonna go ahead and subtract my 4 times x1. Move it to the right hand side. And then we'll go ahead and subtract 4 times x2. And move it to the left hand side. So that means this guy cancels out here. This guy cancels out here, and you are left with 12 minus 4. 8x2 on the left. 12 minus 4. 8x1 on the right. And I know they're like 100 yards apart from each other. But let's finish that here. So you have 8 times x2 equals 8 times x1. What can we do to clean that up a bit? Yeah, very nice. Divide by 8. And this is what we were hoping for, that we could get x2 and x1 to be equal to each other, because if they show that they are equal, so that basically means, yes, we started out with 2 different x values, and we were trying to see if they gave us the same y value or not, and that's why we set our v of x1 equal to v of x2, because we wanted to see, are we going to end up with the same y value, even though if we started out with 2 different x values. But when you get x1 equal to x2, that actually tells you you did not have 2 different x values, you had the same x value, so you, for one x, you only get 1 y value. So this is in a generic term, without having to use numbers for x and trying to see, what kind of relationship you would have. So if you can show that x1 is equal to x2, that means you do in fact have a 1-to-1 function, which means we can find its inverse. So this guy is going to be 1-to-1. And we'll actually talk about how to find its inverse. Oh. Let me save this image. Let's see if that one is saved this way. Do a check. So remember, if my x1 did not come out to be equal to x2, that means you don't have a 1-to-1 function, which means you cannot find its inverse. So having that property of 1-to-1 is very, very crucial if you are going to have an inverse for a function, because if you cannot prove your function is 1-to-1, you cannot prove it's got an inverse. So questions on this example here, guys? Okay, what's that? So this guy was, obviously similar to this example over here. Let's take a look at number 10, just to see how we can show if that is 1-to-1 or if it's not 1-to-1. So same thing. You start with k of x1 on one side, k of x2 on the other side. So wherever you see an x, replace it with x1 or x2, depending on the side you are on. So we would have cube root of x1 plus 9 on the left, and cube root of x2 plus 9 on the right. And again, our goal here is, guys, to show if x1 is equal to x2 or not. So what's the first thing we need to do to simplify both sides of our equation? Before you can even do that?
Give this a room.
Yeah, you gotta get rid of the cube root first, because everything is inside that cube root symbol, and so we cannot add, subtract, do anything till we get rid of them. So since this is a cube root, remember, for a cube, to get rid of it, You have a cube root, for a cube root to get rid of it, you have a cube. So you will raise both sides of your equation to the third power. So the cube root and cube can cancel each other out, leaving you behind with just x1 plus 9 on left and x2 plus 9 on the right. And then what else do we need to do? So that we can show x1 is equal to x2. Very nice, yeah, very good. Subtract 9. And when you subtract 9, you will see those guys cancel each other out, and this is exactly what we were hoping for. X1 is equal to x2 because everything else canceled out, and when we get this conclusion, we know our function is 1-to-1, which means you can find its inverse. As I had mentioned before, and you can again see your video lectures for the solution to number 11, but obviously this guy is not going to be 1-to-1. So as I was saying, having that relationship of 1-to-1 is what we need if we are going to find an inverse. So this example here actually takes you step by step of how to find the inverse of the function, and we're just using the pizza example again. So if x represents the number of toppings for our pizza, we know if you had 0 toppings, that would be 0 times 2, which becomes 0. So your cheese pizza is just $5. And then depending on the number of toppings, you keep adding $2 to your total cost. So if your original function is f of x equals 2x plus 5, remember the main goal is you switch your x and y variables, and that should create your inverse function. So that's exactly what we're doing here. You start out by replacing your f of x with y, so you write it as y equals 2x plus 5, and then literally we are interchanging the position of our x and y variables. And you will see now we bring the x on the outside, you put the y inside with the 2y plus 5, and then all we are doing at this point is getting y by itself. So you start by subtracting 5. Bring it to the left-hand side. So you would have x minus 5 equals 2y because we moved him to the left, and then divide by 2. Get your y by itself. And you will see that gives you your inverse function. So it's literally, you have your original function with the x and y variables, switch the places of the x and y, and then just clean up so that you can get y by itself. And since this is an inverse function, we use that notation of, f to the -1, f inverse, to show that we are talking about the inverse function. So your original was the f, which was 2x plus 5. And its inverse function is going to be x minus 5 divided by 2. This is what we call as the switch and solve method. And they're showing you what happens when you start out with a value for x in the original function. So if you take your original function, replace the x with 3, that means you are going to have 2 times 3, which is 6. 6 plus 5 gives you 11. Take that 11, put it inside your inverse function. So that would be 11 minus 5, which of course gives us 6. 6 divided by 2 gives us 3. So you end up with the same number where you started out with. Remember, that was the composition between the inverse function and the original function itself, and that's kind of what this little illustration is showing. When you do a composition between f and f inverse, or you can honestly even reverse that order and it's still give you this. So that's how the composition between these guys work. And then remember how your domain and range will also switch places. So that's what your switch and solve method is. Literally switch the x and y variable and then solve for y. I think we should have an example to do that. Okay, we've already done this example from the handouts. I'm going to skip him. Ooh, this is a good example. So remember how I told you that inverse functions, when you do the composition with itself, actually gives you an identity function? So that little red line that you're seeing in the center of the graph is actually your y equals x line. So this line over here is that identity function. Remember where you had the ordered pairs of the 2, 2, 3, 3, 5, 5, 6, 6, that's your identity function. So if using that diagonal line y equals x as your reflection surface, if the two halves are looking like mirror images of each other, they are actually inverses of each other. If they are not reflections of each other, then they're not inverses. So I just tell you guys to imagine if we were to fold our graph along this red line, would the two halves coincide? So if you folded that graph on the diagonal on that little red line, would the two halves coincide? The other thing you can do is measure the distance. So talk about, pick a point on the line and talk about, is this distance the same as this guy? Pick another point on the line. Is this distance the same as this guy? You can count the squares in this case and see. So yes, they are actually reflections of each other with respect to that line y equals x. And so in this case, we would say, yes, these two functions are inverses of each other. But let's pick another example and let's see what other options it shows. Now what happens when you try to fold it along that red line? They're not going to be reflections of each other. So this guy is no, this is not an inverse. Oh, is that all your iterations are? I thought they had more. Oh, there we go. So something like this. Would they again be reflections of each other with respect to that red line y equals x? No, they're. So this is again, graphically, yes, it's a nice simple way to see if they are going to be inverses of each other. But again, like we said, we don't always try to depend only on visual methods of finding if they are inverses of each other or not. So yeah, we've got 5 minutes. If you are going to use the switch and solve method, of finding the inverse for your function, start by replacing your f of x with y. So you should have y equals negative x minus 4. Then this is where the switch comes in. So where you have y, replace it with x. Where you have x, replace it with y. And then all you are doing at this point is trying to get the y by itself. So we want to get the y by itself, move everything else to the other side. So we can start by adding 4, which of course will then cancel that out on the right hand side. So let's see, we end up with x plus 4 equals negative y. And again, you don't really want to leave the negative on the y either, right? We usually just leave y as a positive number. So to clean that up, what can we do to make this into a positive y?
Multiply both sides by -1.
Very good. Multiply both sides by -1, or you can also divide both sides by -1, and you'll still get the same result. So multiply both sides by -1, negative times negative will become positive, which is what we wanted. So y becomes positive, and then this guy distribute, which will end up giving us negative x minus 4. What happened here?
It's the same equation.
The same equation. So this is another example of where the function is its own inverse. So your inverse function, and again, using that notation for inverse function, replace the y with that f inverse. Oh, I forgot my x. So he is his own inverse. And there's a couple different functions that do that. But anytime you have a negative x like this guy, you do end up seeing them becoming inverses of each other. So in this case, then it's negative x minus 4. So there is actually a shortcut method that you can use. Safeties. There is a shortcut method that you can use to find inverses also, and we'll talk about that. But you know that example we did with the 12 minus x divided by x plus 4 or whatever that number was? Those types of examples, you do want to use the switch and solve method. Now, for this guy here, we could have used the shortcut method to find its inverse. So we'll talk about that next time. So we do actually have about a third of this section that we still need to finish because we really haven't talked about how to find inverses. So we're not gonna be doing our exam on Thursday. We'll use Thursday to finish chapter 2. If we have time, we'll get into chapter 3. If not, definitely finish chapter 2. So we'll actually move your exam to a week from today, and we'll make it October 1. Next Tuesday. We can't take the liberty of next Thursday, that's too far out. So not on the 6th, but on the 11th, we will do our chapter 2 exam. So again, guys, please work on your homework. If you have any questions, let me know. And I will be able to be back by then, so that will be safe for you also to take the exam. So have a wonderful day, guys. If you have any questions, and I'll see you on Thursday. If you guys have questions online, you can stay back and get an answer. I'll always see you guys on Thursday also. Okay, there everyone, careful. Yeah, Maria, give me 1 second and I go. So I'm just gonna
Bye, thank you.
Yeah, thank you.